Hello students, welcome to our channel Success Achievers. Today we are going to solve one question. Let us see. Find the period of low amplitude vertical vibrations of the system shown. The mass of the block is m. The pulley hangs from the ceiling on a spring with force constant k. The block hangs from an ideal string. Okay, that is, everything is ideal. So we have to calculate the time period. So here we'll use the force law. Okay, force method. So first of all, we'll calculate what is the equilibrium position, what is the tension, those things we'll calculate. So let's see. The whole system will draw here. This is the mass. Here the pulley is, one pulley is having the one side is one string, another side one mass is hang, one block is there, mass of the block is m. Okay, now this is we'll consider at equilibrium position. Okay, now that means it is the main position, now the main position, but I'll draw another diagram here. So this is the natural length. So this is natural length, this part is natural length here. Now this much of expansion happened, this much of expansion happened, this is x naught. Okay, now in this case we'll draw the tension. For example, tension we are taking T naught, this is, and here also T naught. Now upward direction force on this pulley will be kx. So kx naught, that is force in upward direction. Now on the block downward direction force will be mg. Now here we'll see in equilibrium condition for block in equilibrium we can say that net force is equal to 0. Now net force means upward direction T naught minus mg is equal to 0 equation, or further we'll write. So we will get T naught is equal to mg, equation number 1. So next we'll see for the pulley. For pulley, the pulley is always in equilibrium as it is ideal pulley, massless pulley. So net force is equal to 0. Now see, upward direction force is kx, upward direction force is kx naught. Okay, and downward direction T naught, 2 times T naught. Then we can say kx naught minus 2 times T naught, that is equal to 0. Then here we are going to write 2 T naught is equal to kx naught. Further T naught is equal to, we got mg. So equation 2. We'll write from equation 1 and 2. From these two equations you can say 2 into mg is equal to kx naught. So simple way I am keeping kx naught is equal to 2 mg. This is equation 3. Now what will happen when we'll elongate, will displace the mass, the block slightly. Now we are displacing the block slightly from its main position. So everything we are going to draw. Okay, now you will see here everything is same, just this block has moved by one distance x, and this one is x naught already there, this is x naught. Here you can see, suppose this is x1 distance, and this side also x1 distance, definitely this is x1 distance. Now what we have to do, now we'll calculate. Here the tension will be different, this is tension T. Now upward direction displacement will be there, means force constant, spring force will be there, F spring force I am writing. Now in this situation, now net force will not be 0 for both of them. We'll see here for block net force will not be 0, but pulley always will be in equilibrium, because we know the pulley is massless. So though it is in acceleration, it will be in equilibrium because it is massless. Net force equal to mass into acceleration. If mass is 0, whatever acceleration may be, it will be in equilibrium. Let's see. So in this situation, first of all, we'll discuss for the block. Okay, so downward direction mg, it will remain as it is. Then we can say for block, net force is equal to mass into acceleration. Okay, mass into acceleration. So net force is in upward direction, you can see here upward direction tension is there, downward direction mg. So now tension will not be same as previous case, because here it has displaced, so spring force is there some different. So upward direction, downward direction will take as positive because the block has been displaced downward direction, so that direction only we are taking as positive. So take downward direction as positive, downward direction as positive direction, means we are taking the direction of displacement of the block as positive direction. So mg minus of t, that is equal to mass into acceleration. Now this equation will give as equation number 4. Now further, for pulley, now this pulley will be always in equilibrium, so you can say pulley net force is equal to 0. So see here pulley, in case of pulley is upward direction fs, downward direction t 2 times. So then we can say same way again, fs minus 2t is equal to 0, or we can say fs. Here the important point, see how much from its natural length it has been displaced. This is the natural length. Now from natural length, total displacement of the pulley is x naught plus x1, x naught plus x1. So here you can say total displacement, so k into force is x naught plus x1 minus 2t, that is equal to 0, or we can write 2t is equal to k into x naught plus x1. Then t is equal to, we can say, k by 2 into x naught plus x1. So this is fifth equation I am considering. Now you tell me, this fifth equation will substitute in equation number 4. So equation, so now what I am doing, I am writing here, just giving one line here. So equation fifth in equation 4. So what is there? Mg minus t is equal to ma. So mg minus t is how much? K by 2 into x naught plus x1, that is equal to mass into acceleration. Now you already know, we can open this bracket first, mg minus k x naught by 2 minus kx1 by 2 is equal to m into a. Now here what we'll do, we already have calculated, see, equation number 3, k into x naught equal to 2 times mg. So we'll write from equation 3 mg minus 2mg divided by 2, so 2 gets cancelled, minus kx1 by 2 is equal to ma. From equation number 3, then we have mg minus again mg minus kx1 by 2 is equal to ma. Okay, then mg gets cancelled out, so we will have ma is equal to minus kx1 by 2. Now first here we have to find another relation, that is between x1 and x. So we have calculated, see, we'll find here this relation between x1 and x. So this relation we have to find out. So for the mass and pulley system, again I will draw it. Okay, so here few more things we'll see. Here we need to calculate the relation between x1 and x. So this distance is, we know, x, by which the block has been displaced, and this distance we know x1, by which the pulley has been displaced, x1. So we know that here we can write this length is L1, this is L2. There are two methods by which you can calculate. One is total work done by tension is equal to 0. That method also you can use. So here I am using L1 prime, this side L2 prime. Now total length of the string will remain same. So we can say L1 plus L2 is equal to L1 prime plus L2 prime. Now here you can say L1 plus L2 is equal to, now L1 prime, see, L1 prime is equal to, this L1 is equal to x1 plus L1 prime. So that you use, otherwise L1 prime is equal to, you can say L1 minus of x1. So that we can say L1 minus of x1 plus another side. Here also you see, now for this length, so this side increased by x distance, but here you see one more thing, it is decreased by x1 distance. This length, this side is decreased by x1 distance but increased by x distance. So we can say here L1 minus x1 plus x. That means you can say L1 plus L2 is equal to L1 minus x1 plus L2, sorry, this is L2 minus x1 plus x. So L2, L1 both cancelled out. So you are having 0 is equal to 2 times minus 2 times x1 plus x. Or we can say 2x1 is equal to x. That means x1 is equal to x by 2. So we can say the relation is, when the block will move by x distance, the pulley will move x by 2 distance, half of the distance. Okay, so this equation name we can give sixth equation, or this one will give sixth equation. This is sixth equation, and this one will give seventh equation. Now we'll substitute seventh equation in sixth. Therefore seventh in sixth equation, then mass into acceleration is equal to minus k by 2 into, in place of x1 we'll write x by 2. Oh, x by 2. So here we are getting ma is equal to minus k by 4 x. Fine. That means we can say acceleration is equal to minus k by 4m into x, and this is nothing but omega square. So omega square is equal to, you can say, k by 4m. So we will get omega is equal to square root k by 4m, and omega is equal to 2 pi by t, that is equal to square root k by 4m. Then you are getting t is equal to 2 pi square root 4m by k. Now you can take this 4 outside, so 2 will come outside. So time period t is equal to 2 into already 2 is there, so 4 pi square root m by k. So this will be your correct answer. Now check the options. So your option will be, third option is correct. Now another thing I will tell you, okay, one more part I will tell you, that is additional, you can say. Total work done by tension is 0, that method we can use. So look at here, I am just drawing this part. Now few points I will draw. Here one point will take, here another point, here another point, and this point. Now tension is, you know, this way tension. Now this one has displaced by x, this point displaced by x1, this point also displaced by x1, but this displacement is downward, this displacement also downward. Now here we'll see work done by tension, work done by all tensions, total work done by tension equal to 0, because tension is, we can say, as internal force. Now see, here tension downward direction, here also tension. Look at here, tension here downward direction, displacement is also downward direction. So we are taking as t into x. Yes, before that I will take another point, that is this point. You say this point is fixed, here no displacement, the work done is 0, so t into 0. Now plus here displacement is x1 downward, tension is also downward, so we will write t into x1. Here also you see this point, tension downward, displacement downward, you can write plus t x1. And here you see this, for this point it is displacement is downward x, but tension is upward, so minus tx, that is equal to 0. So we can say here 2t x1 minus tx equal to 0. So t we can take common and it will be 0. 2x1 minus x equal to 0, so x is equal to 2x1. So this is the relation. Okay, so thank you for watching. Please like, share and subscribe.